Welcome to my channel Euclid Mathematics and yet another video on ring theory. I have started a lecture series on ring theory, so you can see my more videos on playlist. So if you want more concept and more previous year questions, all videos are added there in a playlist. So in my today's video, I will explain one of the important topic from ring theory, which has a lot more weightage in a different competitive exam. So like M.Sc exams, like Net, CET, GATE, other exams also. So this topic is more important. Okay. So now let's get started our today's lecture with the topic irreducible polynomial. So I will give little idea about the reducible polynomial also. Okay. So first of all, let's see what is meant by irreducible polynomial. Okay. So we have the R is an integral domain. Okay. So we know that the meaning of integral domain. Okay. Commutative ring with unity and two their element, their product non-zero, and that means these two elements are also non-zero. Okay. If these two elements zero, that means one of the element is need to be a zero. So this is the definition for integral domain. So that means R is an integral domain. R satisfies the property integral domain, a non-zero non-unit element, non-unit polynomial. Okay. So now R is here as a ring of a polynomial, okay, or polynomial ring, which we learned in our previous video. So if you wanted to know what is meant by polynomial ring, you can see my previous video. Okay. So here you can see that a non-zero non-unit polynomial. Okay. So we have there f of x is a polynomial which is a non-zero and value it is a non-unit. Okay, and which is belongs to a ring of polynomial. Okay, so R of x is said to be irreducible polynomial. So when we say that polynomial is irreducible, okay, when we write that f of x into product of two polynomials like a g of x into h of x, okay, this is a product of that two polynomial. So we write that f of x is as a g of x into h of x. Now here one condition need to remember that g of x and h of x has to be there in R of x. Okay, so it has to be there in R of x. So if this property hold, then either g of x is unit or h of x is unit. One of them has to be a unit. That means one of this g of x has the value for unit element and h of x has to be a value for unit elements. That means in simple language, we cannot factorize our polynomial. Okay, that means one polynomial has to be a unit and another is a non-unit. That means that we are not able to find out their factor. Okay, or if we are able to find out that factor, okay, if we are able to find out the factor and none of them is unit and both does not belong to R of x, so then we also call it as the irreducible polynomial. Okay, so it is easier to understand what it is here. If we can factorize that polynomial, that is belongs to in a ring, and that means one of them has to be a unit element. Or second definition, we can factorize that polynomial and these two polynomial are having none of one is a unit and none of these are unique. That means these two are not belongs to our ring of polynomial. Then we say that is the irreducible polynomial. Okay. So this is quite easy to understand. Once we solve example, we come to understand that what is meant by irreducibility. Okay, so there are several irreducibility criteria also. Okay, like Einstein criteria, mod p test. There are so many tests are there that we can check our polynomial is irreducible or reducible. Okay, so now let's get started our example that we all can understand easily the meaning of irreducible polynomial. So here you can see f of x, we have polynomial 11 plus 33x square, which is belongs to, okay, integer polynomial. Z of x means integer polynomial, which polynomial is having integer values. Okay, so which include z of x is reducible over q or not. Okay, so we have to check that polynomial which is belongs to z of x, and we have to say check out whether that polynomial is irreducible over q or not. Okay, so we have to check it now further. So we know that the definition of irreducible polynomial, it says that we can write that polynomial in the product of two different polynomial and one of it has to be a unit element. So I written here f of x is 11 plus 33x square. Okay, so take 11 common from here, that bracket 11 common here, so under it is remain 1 plus 3x square. Okay, so 11 ones are 11 and 11 threes are 33. Okay, so our original polynomial remains same. So f of x, it can be written as g of x into h of x. Okay, so we know that g of x is a constant, so we call it as the unit in q of x. Okay, and this one is the remain polynomial. Okay, so here we call g of x as the 11 and 11 which is belongs to q of x. Okay, 11 is the part of a rational number. Okay, so g of x is equal to 11 which belongs to q of x. And now further h of x we have here 11 plus 3x square. Okay, so we can see that the polynomial in a rational also. Okay, that means q of x is the part of rational polynomial. Okay, okay, so here h of x is a part of rational polynomial. So g of x is 11 and h of x is 1 plus 3x square. So we factorize these two one. Okay, in the form of g of x and h of x. So g of x is 11 is a unit element in q of x. Okay, so this one is a unit element in q of x and h of x it is here 1 plus 3x square. Okay, so other factor it is here. So if this hold, one of them has to be a unit and another one is a polynomial. One of them is unit and another one is a polynomial. Then we say that our f of x which is l1 plus 33x square is irreducible over q. Okay, it is the irreducible over q. So this one is my first example for irreducibility over q. Okay, so I hope so you all have understood that first example. So for second example, here in my second video, I will explain the polynomial which is not irreducible, okay, and which is irreducible, okay. So I have polynomial here, okay, 4 plus 2x square, which is f of x. I consider that polynomial. So I have to show that the irreducible over q, but not irreducible over z, okay. So let's find out how we can show some polynomials which are not irreducible or which is irreducible, okay. In my previous example, I explained that the polynomial which is irreducible over q, okay, which is irreducible over q. But now in this example, I will explain the polynomial which is not irreducible also, okay. Now I have here polynomial as per the definition. We can write that polynomial into g of x into h of x. Take 2 common here. G of x is a 2, h of x is this one, okay. So f of x can be written as g of x into h of x, okay. So this is the expansion for f of x is g of x into h of x. Now g of x is here 2 and h of x is here 2 plus x square, okay. Now here you need to understand we have to show irreducible over z, okay, and irreducible over q, okay. So we can see that 2 which is irreducible over q. Why irreducible? Because one of them has to be unit, and the definition of a unit, it says that every non-zero unit element which has a multiplicative inverse in our given ring, okay. So here we have q given, so we can say that 2 has an inverse 1 upon 2, which is belongs to q. So it has a multiplicative inverse in a q. That means the 2 is a unit element in a q, okay, but not in a z. Why not in a z? 2 has a multiplicative inverse 1 by 2, which does not belongs to z. Integer does not include 1 by 2, okay. So it is not unit element in a z, but it is a unit element in a q. So obviously it goes to irreducible over q, but not irreducible over z, okay. So you can see that g of x is equal to 2, which belongs to z, and h of x is equal to, this is also belongs to z, but neither 2 is unit nor 2 plus x square is unit. Why it is not unit? Because unit element says that it has to be inverse in our given z of x, okay. So you can see 2 has 1 by 2 inverse, which is not belongs to z, so it is not unit. And 2 plus x square, it is having inverse 1 upon 2 plus x square, okay, which is also not in z, okay. So these two do not have unit in a z, okay. So we can say that f of x is equal to 4 plus 2x square is not irreducible over z, okay. Now let's check for the q of x, okay. So q of x, I did same procedure here for q of x. So return g of x 2, h of x 2 plus x square, okay. So g of x is a 2, h of x is a 2 plus x square. Now we know that g has a multiplicative inverse 1 by 2, okay. That means it has a inverse, so it is a unit element, okay. So definition of unit element, it says that it has to be inverse in given ring, okay. So here you can see g as a 2 1 by 2 inverse, okay. It is a unit in q of x, and f of x is equal to this implies that one of it has a unit, okay. So this implies that f of x is equal to 4 plus 2x square, which is irreducible over q, okay, but not over z, okay. So this one is a very easy definition. We just have to apply on our example, okay. I hope so you all have understood my today's lecture, which is on irreducible polynomial, okay. That we need to remember only the definition of irreducible polynomial, okay. It's quite easy to understand, okay. I hope so you all have understood my today's lecture. If you have any doubt, comment me in comment section. I will upload similar videos like this, and if you want more videos, you can check it into my playlist, okay. Thank you everyone. Thank you for my today's lecture.